Okay. We have the problem, I think it's number 30 in section 12.6. We have a uniform lamina, circular lamina of radius A. Now there were a couple of errors in what I saw, and it was set up in polar coordinates, and as we see, even if you set the thing up in rectangular coordinates, you end up with about the same integral you do if you set it up in polar coordinates, so there's no real error in that. But I'm going to set it up, I've set it up in rectangular coordinates, and I'm using a rho for the density. Delta might be, small lowercase delta might have been a better symbol, but I'm used to using rho. But since we're into things that involve spherical coordinates, probably should have used delta, but we can live with the rho. So, in calculating moment of inertia about the y-axis, the idea simply is let's find a locus of points where all the points are at an equal distance from the axis. Well, that would be vertical lines in this case, lines parallel to the y-axis, which means it's natural then to partition the x-axis and then to take strips, vertical strips, corresponding to each partition, calculate the moment of inertia of each, and set up the integral. So I've done this, I've partitioned the x-axis, and the typical interval within my partition is going to be of width delta xi, and it's going to contain a sample point xi star. Well, if the sample point is xi star, that's how far the sample point is from the y-axis. It's a thin strip, so every point is about that far from the y-axis. And when we do our limits, of course, that's going to take care of any little inaccuracies we have due to the location of the sample point within the interval. Okay, well anyhow, if the sample point is xi star, then we construct this triangle to determine how wide the strip is. Okay, so there's the triangle, and here's the expression. The Pythagorean theorem gives us this expression very simply: square root of a squared minus xi star squared, if you can't read that. And then it looks like I've got an error in what I wrote here. I'll fix it as we go. Okay, so the width of this entire strip is double this, and I don't think I doubled it when I wrote this out. Okay, so the width of the strip is 2 times the square root of a squared minus xi star squared. Its area is therefore that times the delta xi, length times the width, and the mass within that is the density times the area of the strip. I should have had a 2 here. Okay, so there's a 2. So that the contribution to the moment of inertia is what? It's the mass times the square of its distance from the axis of rotation. So we just multiply this expression, which should have had the 2 in it, and we insert this xi star squared, xi star being the distance of the sample point within this interval from the y-axis. And here's our contribution to the moment of inertia. So, correcting this slightly, now the 2 rho can come out of the integral. You end up with the integral of x squared times the square root of a squared minus x squared, which you're probably going to do using a trigonometric substitution, which then makes the whole integration equivalent to the integration you do if you set it up in polar coordinates, where the distance from the axis of any small increment out here is going to be r sub I sine of theta sub I. Okay, in any case, one way or another you get this integral, and you do it, you work it out, and I believe if you work this integral out, you're going to get something in terms of rho. But now, let's figure out what the problem asked for the result in terms of the mass m. And the error I saw, the main error I saw was that m was used as if it was the density. So let's look at the correspondence between the density and the mass, and it's very simple. If the density is rho, then the mass is pi a squared, the area, times rho, which is m, so that rho equals m over pi a squared. So when you get your result here, you replace rho either before or after by m over pi a squared, and then you end up with the ma squared over 4. Okay? Now I wrote this out carelessly 3 or 4 times, because you can see the little erasures here. But writing it out carefully, we have here now the ring, but now we're rotating it about an axis through the center. So the ring is rotating like this, instead of in this case where it's kind of like this, it's rotating in this way about the axis. So a typical ring has a width delta r, and I could call it delta r sub I, it's a little more general, times ri star, or at ri star, at distance ri star. So this distance out to the sample point in the ring, which I haven't labeled, is your ri star, and that should be obvious. So there's the ring area. The total mass of the ring is pi times rho a squared, and that's what we call m, so that rho is m over pi a squared. And we're going to use that when we set up our, well, at some point we're going to replace rho by m over pi a squared, so that as we did here, we get a result in terms of m. So I'm leaving rho here because the expressions are a little simpler with rho, but at the end, we want to get things in terms of m, which is ultimately simpler. Okay, so delta I sub I, the moment of inertia contribution of the ith subinterval, is then just ri squared times the mass of that interval, okay? And I never did write the mass of the ring, mass of the increment, but it would be just rho times the area. So we see here in our delta I sub I, we see the area here, same as this. We see the ri squared for the squared distance from the axis, and we have the rho here. The rho times the area gives us the mass, which we multiply by r squared, ri squared in this case, giving us this sum, which approaches this integral, which comes out very easily to be pi rho a to the 4th over 2. But since rho is here, okay, same expression here and here, is m over pi a squared, we replace rho by m over pi a squared. We get ma squared over 2. Now, there's another reflection here that there's a difference in the moment of inertia if we rotate about the center as opposed to the y-axis. This is because when we rotate about the y-axis, on the average, the points of this lamina are somewhat closer to the axis than they are here. And you want to convince yourself of that. That's what gives you the difference between the ma squared over 2 and the ma squared over 4. And it turns out that on the average, the points here are square root of 2 over 2 times as far as they are here. Now, square root of 2 over 2 is less than 1, it's about 70%. Okay? So that when you square your distances, you get the square distance, in this case, being half of what it is, square distance of the average point in the circular lamina from the y-axis is half as great as it is about the, as the average square distance from the center. And there are lots of ways you can convince yourself of that, and that's worth thinking about a little bit. Okay, now these moment integrals are extremely important. You want to do the integral for the sphere. I think that's probably in the problem set. I don't know that I've seen it, but it's worth doing, okay? Just like the volume of the sphere in all the different coordinate systems. Do a lot of moment integrals. They come up all over the place in probability, in other areas of mathematics that aren't necessarily applied to physics. They're extremely important.